suppose I have a register, okay, and let us assume it is storing 4-bit data, okay, and suppose the data that register has stored, let us assume it is 0110, okay. Suppose if I want to shift this register in the 1-bit left, okay, 1-bit left means what? I just wanted to shift in this direction. So the data will be there are two kind of data, right? See, so the data can be this 0. Yeah, let me make it properly for simple understanding. Later on I will tell you. This 0 can be shifted to this one, LSB. So the resultant data will become, this one will come here, this one will come here, this 0 will come here, and this 0 will come at this point. So I will get 1100 kind of data. So basically the shift registers are nothing but if I want to move data in any of the direction, either in the left direction or in the right direction, we can call those registers as a shift register. What is the importance of a shift register? I will tell you later on. Okay. Sometimes let us try to take a simple example. Suppose I have a register having data that is stored like 0100. Okay, 0100. Now, if I want to multiply this, yeah. So if you can convert this into the equivalent decimal number. So the decimal of this 0100 is nothing but this is the 4. Okay. Now, suppose if I want to multiply this number by 0100 is multiplied by 2. Let us assume I want to multiply it by 2. Yeah. So this is the operation which I want to perform. I want to multiply it by 2. In that case, what I have to do? I have to use a lot of number like 0000 0100. Then I have to add 0, and then yeah. So what I have to do? I have to replicate this one. I need one half header here. Then I need one full header here. I need one full header here, and then I will add one half header over here. So for this purpose, I may need 2 half header, 2 full header, and 8 number of AND gates. Okay, so this much of hardware is required for this operation if I want to simply multiply this number. But sometimes there are some possibilities, like suppose if I can rotate this number 1 bit to the left, then what output it will give? Let us try to see here. The output that I will get 1000, and this is nothing but this is equivalent to 8, and this is what we want. If I have to multiply it by 2, just rotate by 1 bit in the left direction and you will get the product output, or multiply by 2 output. Okay, so this kind of some of the applications where we can use it. Okay, so these are important things. Now let's talk about what are the different types of shift registers we can have. Okay, the first kind of shift register is the serial input, serial output. I have already listed before. Okay, the first kind of shift register is the serial input, serial output shift register. Okay, in this shift register we can have a clock pulse, we can have a clear pulse. Okay, so the clock pulse and clear pulse, you know what is the role of these two things. And then we can have an input which will provide the serially data. Okay, if you can go back to the previous slide, whatever we studied, parallel load one, we are providing the input to all the flip-flop parallelly. So that, and we are taking output parallelly. Okay, so that kind of register we can say that register is nothing but that is the parallel input and the parallel output. Okay, so let me go back to that one. Can we also shift data bits multiple times using shift register? Yes, of course. It is not necessary that I have to use I have to shift only one time. It depends on how many times you are giving the clock pulse. So at each clock pulse, that will be shifted in that direction by 1 bit. Okay, either in the left or right. Okay, so this is possible. Okay, so let me go back to the this slide. If you see this slide, here we have 4 inputs, A0, A1, A2, A3, and 4 output. If you can clearly see here, all the inputs are parallelly given to the flip-flops, and all the outputs we are taking out from the flip-flop. So this kind of flip-flop, this kind of arrangement of this kind of register, we can say parallel input and the parallel output. We are performing input and output. We are giving input parallelly and we are taking output parallelly. Okay, so we can call, or this register will fall in the category of parallel input, parallel output kind of structure. Okay, so yeah, so that was the example. Let us now consider what is the serial input, serial output. So in the serial input, serial output kind of structure, I can provide input to only one flip-flop. Okay, either on the left or right. Okay, so I can provide the input to only one flip-flop, and I have to take the output from only one flip-flop. Okay, so what does it mean? What is the complexity? I will tell you, because I have to perform only one bit at one clock pulse. So how much time it will take to get the output, that depends on how many, that depends on what is the size of register. Suppose I have an 8-bit register, so it will take 8 clock pulse to get the output here, because it is serially processing the data and we are serially taking the output. So to get all the 8-bit data which we have provided at the serial input side, that will take 8 clock pulse to execute it. Okay, so this is the delay and other things, and this is the importance of this serial input, serial output kind of registers. Now let us talk about the second category, which is the serial input, parallel output register. All other things are same, only output will be taken out of parallelly. So the input will be given serially and the output will be parallelly. So initially what will happen? Initially 0 0 0 0, let us assume it is a 4-bit. So 0 0 0 0 will be given, output will be 0 0. And now let us assume I am giving the input pattern which is like 0 1 0 1, something like this. So in the during first clock pulse, this 1 will be transferred at this one, so I will get 1 0 0 0. In the next clock pulse, this 1 will be shifted here, and now this 0 will come to this point. So 0 1 0 0 will be the output. In the next clock pulse, this 1 will be shifted here. So 1, this 0 will be shifted here, 0, and this 0 will be shifted here, and the next term, that is 1, will come out. And to then in the next state, I will get 0 1 0 1. So if you see here, the time taken by this serial input, parallel output is also same like this one. The number of how much, the exact data whatever we have, that will take that much of clock pulse time to reflect at the output side. But the only thing is, one by one we can start reflecting the outputs, so that we can see initially whatever the clear was there, but it will start loading the things one by one, and it will again start shifting in one of the direction. Okay, so this is possible in here in this case. But yes, again, it will take the same time to reflect all the inputs whatever we have, all the input data which we have. So it will take the same time. Okay, next one is the next kind of the register is shift register is the parallel input, serial output. In this case, what we have to do, we have to provide the data parallelly, but I have to take out the data serially. So only one flip-flop is responsible to give the output, but I am loading the data parallelly to the registers. So this is also one of the possible. I will tell you how it looks like. Okay, and the next category could be the parallel input, parallel output, which we have already seen in the previous slide. Okay, so the parallel input, parallel output kind of arrangement is here. So the minimum time will be taken by this kind of register, because all the data bit will be loaded and that will be transferred parallelly. So a single clock pulse may be sufficient to execute this operation. But for this one and for others, for also this one also, you need and how much time it required, that depends on what is the size of this register. If it is 8-bit register, it will take 8 clock pulse to give the exact output whatever we have. Okay, so this is the importance. Now this is all about the simple registers. Okay, now let us talk about the shift register, how the shift registers looks like. Okay, how we can rotate the things serially. So rotate, so we can have a clear pulse, clock pulse. Now rotate right serially means I just told you the last bit that will be rotated to the this one. So and this the first this MSB will come to the next MSB, next MSB will go to the next MSB, and so on. And then LSB will become the MSB. Okay, so this is how we are rotating the things here. Similarly, on the left rotation is also possible, but the direction will be opposite. So here the direction will be in this direction, and the data will be rotated in this direction. And yeah, of course, we can combine this rotation feature as well as this data loading feature. Okay, so this is possible, and these are the different kind of shift register that we can have. Okay, so if you have any doubt, you can ask the questions. Otherwise, we can move ahead. Fine. So let us consider first example, first kind of serial input, serial output shift register and left shift register. I'm talking about the left shift register. So how the structure will look like? Let us try to see. Serial output, serial input means there will be only one input, only one output, and the shifting will be in the left direction. Okay, left direction means what? The MSB will become LSB, and the LSB will move towards to the MSB. So this is what the left shift is. This is the meaning of left shift. Okay, so see here, this is a circuit of the serial input, serial output register. Okay, here because I just told you the MSB like LSB will shift to the next MSB, something like that, and the most significant bit will be taken out. So from there I have to take out. So the output will be taken from the most significant bit. So the Q3 is nothing but this is the MSB. This indicates the MSB. Okay, so this flip-flop, yeah, so let me change the color. This flip-flop represents the MSB and this flip-flop represents the LSB. Okay, now how this will perform the operation. So I have to take the output from the most significant bit because we are shifting in the left direction. So suppose I have a 4-bit register, so 5-bit, whatever the register I have, if I have to shift in the left direction, what it means, MSB will come out and the input will be given to the LSB side. Okay, so here the input has been given to the LSB side and the output we are taking from the LSB side. Now what we need like the output of the first flip-flop that should be connected to the input of the next flip-flop, because this will be transferred to this one, this will be transferred to the next one, this will be transferred to this next one, and this will be transferred to the next one, and from the MSB I have to take the output. So the important point of consideration here is I need to take the output of the LSB and that will be connected to the next one. Okay, and this is what these lines are doing. Okay, so the output Q0 is nothing but this is equivalent to D1. Q1 is same as the D2. Q2 is same as the D3, and the Q3 is nothing but this is the output. Okay, so this is how we are providing serially whatever the data I will give here, 1010 whatever, that will be loaded in the first flip-flop and that will shift in the left direction because the outputs are connected in such a way that the LSB will transfer to the next one. Okay, so this is how the serial input, serial output works, and this is how it is shifting in the left direction. Okay, so this is nothing but this looks like, yeah, this arrangement is the set of flip-flop that can act as a left shift serial input shift, serial output shift register. Okay, if we can try to make the timing diagram. So initially let us assume the inputs are 0 0 0. Okay, but in the next clock pulse let us assume the D in becomes 1. So this D in is 1. So when this positive edge will come, then what it will do, it will reflect the Q0 to the 1. So the Q0 will become 1 and Q1, Q2, Q3 will remain same because they are shifting in the series. Okay, so to reflect this input to the Q3, you need 4 clock pulses. The 4 clock pulses are needed to reflect this D into the to take out the data. Okay, so this is what you should understand, and this is how the timing diagram looks like. This is quite easy, not that much difficult. And similarly, yes, how it is shifting, I have already explained it, so I don't need to explain this table how I have made it. Okay, so this at each time, instead of time, the data will be shift in the left direction. Okay, so this is how serial input serial output shift register works. If you have any doubt, you can ask the questions, because all the circuit what I will explain here, those all are similar, like those all are same, right? So there is no problem as such. If you are able to understand the fundamental of one register, then it is easily you can understand all others. Okay, so this is possible. Similarly, let us try to change the logic. Like I want to make a same kind of register, like serial input serial output left shift register, but with asynchronous loading. What is the meaning of this asynchronous loading? Let us go back to the previous slide. In this slide, what we are doing, whatever the data we have loaded here, that will move in the left direction, and we are not clearing anything. Like all the flip-flops are getting clear at the same time. If the clear pulse is 0, then all the data will be cleared, and if it is 1, then it will perform the shift register kind of operation. Okay, so it will shift the data in the left direction. But sometimes if you want to change something asynchronous way, in asynchronous way, in that case, the clear and the preset input, that is fine. That clear input and the preset input play a major role. Clear is fine because I have to clear this data to all the out here, or whatever the things over here is. Okay, now suppose I want to change the data. Let me go back to the previous slide, then you will be able to understand. Whatever the data D input I have given here, it will be reflected one by one. So see here, to get this one at the D output, I need 4 clock pulse, and all other will be shifted whatever the data input we have. But in between, if I want to give the data, like to preset the data in between without waiting for the 4 clock pulses, so this preset input can play a major role. How it can play a major role? Let us try to see. Here we are giving the serial input. Yeah, this term is nothing but this is the LSB, and this is the MSB. Okay, so here Q3 is there, here Q0 is there, so that is why we can say this is the LSB and this is the MSB. Now, whatever the input I will give here, that will be shifted in this direction. Okay, don't say this is the right shift. Okay, this is not the right shift, because it is shifting towards the MSB, so we can call it the left shift only. It looks like it is shifting in the right direction, but it is not, because it is moving from LSB to MSB. So LSB to MSB movement we can call then the left shift register. Okay, and vice versa. Okay, now what happens if to make it preset means what? I have to, whatever the data I have stored in this flip-flop, I need to make it logic 1. Okay, this is the role of preset. So if sometimes if I want to preset any of the flip-flop in between, then what we can do? We can do something like I want 1 here to preset this flip-flop. Let us assume I want to preset this flip-flop 1. So I want PR complement, that should be 1. And to make this 1, I have to make this we know that what is the rule of this AND gate, NAND gate. Okay, so based on this A1 and the loading, I can decide whether I can preset it or not. Okay, so if you see the truth table of the preset NAND gate, like it is like A and B, so 0 0 0 1 1 0 1 1. A is nothing but AI here we have, and B is nothing but this is the load. Okay, so these are the 2 inputs which we have. And if you want to get PR complement here, so this PR complement, like we know that the output will be 0 means NAND gate means this will be 1 1 1 and 0. This is the output of NAND gate. So if I have to preset it, in that case, I need to make this output 0. So AI and the load, both the signals should be 1. Let me repeat it again what I'm saying. To preset any of the flip-flop, this PR complement should be 0. Okay, because this is the active low. Okay, and if I have to make this one, so A1 and the load should be at logic 1. Okay, so if it is like that, this will give you the 0 and that will preset, and with the asynchronous kind of, we can change the memory or change the data in any particular flip-flop. That depends whatever the controlling we have here. So A0, A1, A2, A3 are not the input. Remember, this A1, A2, A3, these are not the input. They are the controlling signal that decide at which time I have to, or which of the flip-flop I have to reset or I have to preset. Okay, so these are the control signal kind of. Okay, so this is how this serial input, serial output register works. If you have any doubt on this, you can ask the questions how it is working. So this will be preset if the conditions are like this, like load signal is 1 and the input is 1. So if A1 is 1, so this flip-flop 1 will be preset, that will become 1. It does not matter whatever the input we have, immediately it will be preset. Okay, so this is how this works. So yeah, this is the block, and this is how you can prepare the truth table. So I think explanation of truth table is not needed. I have already explained it, how it is working, so you can understand how it is, how we can understand the things. Okay, anyone has any doubt on this asynchronous loading, you can ask the question. Simply asynchronous means, like, if I want to preset any of the flip-flop, I have to just activate this load and I have to activate that control signal, and that will be preset. Okay, so even though it was 0 or 1, it does not matter, it will preset to high. So this is how we can, asynchronous kind of loading is possible. Okay, so this is what we can have. Now let us talk about the write shift register. Okay, remember, let me go back to the previous slide that is needed actually. So see here, in the left shift register, what we have done, we are providing input to the LSB side. Okay, so sorry, to the MSB side. So this is the MSB side and this is the LSB side. Okay, so we are providing input to the MSB and we are taking output from the LSB. Now if I have to make the write shift register, then what will happen? I have to take out the data from the MSB side. Okay, I am saying opposite. No, I just made a mistake here. This is the Q3. Okay, this is the MSB. Sorry, MSB and LSB. So in the left shift register, I have to take out the data from the MSB, and if you talk about the right shift register, in the right shift register, we have to take the output data from the LSB. That's it. This is the only change that is needed. So properly see the diagram, this diagram, and then we will try to replicate it on the right shifting. Okay, so what we are doing here, the outputs are connected to the input and they are shifting in the left direction. Now let us consider that circuit, which are the right shift register. What we are doing here, we are giving input to the MSB side. So the data is we are giving to the MSB side, and we are taking output the data from the LSB side, and the output of the most significant bit is connected to the next one. That's it. This is the only difference. Okay, so the input and output kind of the positions are changed, rest all others are same. Okay, so the MSB output will be connected to the next MSB. Next MSB will connect to the next MSB, and the last one is connected to the LSB. The last one will be connected to the LSB. So this is the only difference that we have between the left and the right shift register. Okay, and the truth table, again, if you try to make the truth table, or the timing diagram, this will like the first bit that will be reflected will be the MSB. So in the previous one, means the left shift one, Q0 was reflected first, then Q1, then Q2, then Q3. But here, first Q3 will be reflected, then Q2, then Q1, then Q0. That's it. This is the only difference between these two. Rest all others are same. Okay. So which of the output will be reflected at each clock pulse? That depends what kind of register it is, whether it is the left shift register or it is the right shift register. Okay. And similarly, yes, this is how the truth table you can make. This is easily doable because we have already done it. So initially, yeah, this truth table is nothing but this is the other way of representing this timing diagram. Okay, so at time instead t0, let us assume the data was 0 0 0 0, and at t1, if I'm giving the data input which is 1, so that will be reflected and rest all other will be, yeah. So if this is the data input, so this one will be shifted to the d3, then 0 0 0. So these all 0 will be shifted 1 bit here. Okay, so here they will be shifted here. Okay, and then and so on. So this is how the shifting is possible here. So this is very easy, so I do not need to explain it in the detail. So now let us try to recall it. Suppose if I want to make the bidirectional serial input serial output register, then what we can do? Okay, we know that if we can recall the left shift register and the right shift register, the only difference was in the left shift register, input was given from the MSB and sorry, in the LSB, and the output was taken from the MSB. So this was the left shift register. If we talk about the right shift register, the input was given to the MSB. So let me write it. Input, output, and left and the right. So in the left shift register, input was given to the LSB and output was taken from the MSB. And if I'm considering the right shift register, so it will be something like this. So let us try to see. Suppose this is the combination. This is the only difference between these two. So if I want to make any register which can perform bidirectional kind of operation, either left or right, so how we can make it? So let us try to see how the circuit looks like for the bidirectional one. Okay. See here. As we know that multiplexers are one of the circuit that can decide which of the input or will be transferred to this one. See here, if the bottom part is common in both. Okay, bottom part is common in both. Now, whether I have to give input to the Q3 or I have to give the input to the D3 or input to the D0, that depends where I have which kind of shifting I want. I just told you for the right shift register, I have to give the input to the LSB. Okay, so this is the requirement. So based on your requirement, whether you want to make it the left shift register or the right shift register, you have to decide whether I have to give input in the left direction or in the right direction. That's it. Okay, so let us try to see how it is working actually. This is the serial input. Okay, the serial input I can see here that this control signal decides whether I have to perform this the left or the right. So let us try to see if this control is equal to 0, then what will happen. Okay, if this control is equal to 0, I01, I01, I02, I03, I04, these 4 will be selected. And if these 4 will be selected, what it means? This I01 is nothing but this is connected to the serial input. Okay, so the I01 is the serial input, and whatever the output I am getting, this is going to connect to the left or the least significant bit. because this one, this D0 is nothing but this is the LSB. And what it means, the serial input is connected to the least significant bit. And if the serial input is connected to the least significant bit, what it means, we are shifting in the right direction. Okay, so if the control is equal to 0, then the right shift is possible. Okay, so this is how we can check it out. Now let us talk about the other case. If the control is equal to 1, okay, if control is equal to 1, in that case, this one, this one, this one, and this one will be selected. Okay, what it means, it means that whatever the input I have here, those will be taken out here. Okay, now let us try to see here. Here I14 is nothing but this is connected to the D input, and this output is connected to the D3, which is the MSB. What it means, the input is given to the MSB, and if the input is given to the MSB, what it means, it will shift into the right direction. I think I made mistake. In the previous one was the left shift register, and this one will be the right shift register. Okay, so let me repeat it what I did. Okay, so suppose if the control is equal to 0, means I01, I02, I03, and I04 will be selected. Okay, and if I01 is selected, what is it means, the data input is connected to the I01, and this I01 will be transferred to the output, and that output is connected to the least significant bit. What it means, we are giving input to the least significant bit, and we are moving data into the right side or towards the MSB. So again, yeah, this is simply left shift register. Okay, now if the control is equal to 1, then I11, I12, I13, and I14 will be selected, and the serially input that will be connected to the I14, which is the most significant bit. So it means that will be connected to the D3. So this will perform in the other way. Okay, so this is how we can design a same circuit as a in the bidirectional way. It can be act as a left shift register or right shift register, and that depends what is the status of this control signal. So the control signal decides the direction of movement. Okay, I'm giving 1 minute time to understand this circuit. If you have any doubt, you can ask the question. See, clear and the clock pulse, I'm not considering this because this is common for all the circuits. I'm only interested in the and of course the input or the control signal of this mux that decides like when I have to activate this mux. Okay, and which of the input I have to select. So based on this controllability, I can decide. So the lower part is nothing but this is the register, and the upper part is the control unit, like that decide the what kind of shift register I have to make it. Okay, so let me write few things here that will be important. If C is equal to 0, okay, if C is equal to 0 means the input are given to the D0, so left shift register. If C is equal to 1, then right shift register. Okay, so this is the important thing that you should understand.